Well, that was mercifully short. What I requested was that they say, he's old, he's had a lot of jobs, here he is. But I do appreciate that, and it's truly an honor to be here. If you look at the list of previous lecturers, I'm quite honored to be included amongst them. You know, in my checkered employment history, I've had an opportunity to know less and less about more and more. So as the topics have broadened, I've had a chance to explore lots of things, and that's been the fun part of the jobs that I've had. So what I want to do today is to just talk about the global energy system. It's big, it's complicated, it's fascinating, it's hard to predict exactly what will happen. So I won't try to do that, but I will talk about the transition that I think is underway in the world now, and well underway, and then try to anticipate the kinds of things that might happen going forward. So if you think about the energy challenge, it really has three parts: economic security, environmental security, and what I would call energy security. And so let me just say a word about each of those. On the economic side, energy is woven through every aspect of modern society. So a good exercise, if you want to think about this, is to, when you wake up in the morning, think about everything you do during the day, make a list of how you used energy. Did you take a shower? Did you use your toaster? Did you get in a car and drive to someplace? I mean, on and on and on. You can do that on your own, but it's hard to live in modern societies without taking advantage of energy, and those costs are embedded everywhere in what we do. It's typically in the U.S. 6 to 8% of the GDP, so that's a big number. And I would just say that economies that are efficient in the way they use energy, particularly cost-wise, are ones that are economically competitive in the world, and that's something we want. And then I would also observe that, look, cost matters here. Energy is supplied and used as a commodity, so one of the things that we in the research community need to do is to work on ways to bring costs down, to make things more efficient, and everybody will benefit. I would also say that we have a responsibility, I think, as humans, to work on energy access around the world. Somewhere around 1.3 billion people don't have access to electricity now. We've made lots of progress in poverty around the world, but that number really hasn't changed over the past decade. So there's a chance to work, and of course I know many of you who have worked internationally, there's a real opportunity to do better than that, and particularly in sub-Saharan Africa and developing Asia. And we should add that to our list of important things to do. Energy security is a part of what we do. Some of us in the room are old enough to remember the oil crises in the 1970s and the long gas lines and the disruption that caused economically. If you look at the price of oil here, you can see the various spikes at times of what kinds of things have been induced there. And then, of course, we've just been reminded recently this is a picture of Hurricane Maria cutting across Puerto Rico, and the devastation of houses and buildings and all of that's one thing, but taking down the grid really does move them back in a very bad way. So we need to work on that. Balance of trade matters to countries, and of course we need to pay attention to the cybersecurity side of all of this as well, because it now is, as we've made systems more automated and communication linked, that creates potential vulnerabilities that we have to worry about as well. And then the third item on the list is the environmental security side. Air quality is a challenge in some parts of the world. This is not a new challenge. I grew up in Houston, Texas, and I can tell you in the 1960s, we had our issues with air quality there. Los Angeles, Pittsburgh, it probably was never bad here, but we certainly, this picture is, I think that's Beijing, yes. The air quality can be a problem there. And it's health related, so doing something about that is important. It's also true that the evidence for human-induced climate change is now, in my view, overwhelming and incontrovertible. And while there are plenty of details that we're still sorting out on how fast and it's not whether, but how much and how fast, we know enough now to know we need to do something about this. And energy is a primary driver of both of these issues. So we need to work on clean energy options that can mitigate both of these sets of problems. So you say, okay, fine. What kinds of things are we trying to change? Well, right now, of course, 85% of the energy we use around the world comes from fossil fuels. And those are carbon-based. And if you look at carbon emissions, they really have grown quite a lot in the last 2.5 decades or so. But the interesting thing is that they have been kind of flat here for a while. Now, part of that was due to a global recession. That's not how we want to do this, that it would be better to not to take that tack. But at the same time, there is some evidence that we're beginning to transform the system. And so we might ask how that works. The first thing to think about is it's not just the emissions where they happen, but we move carbon emissions around the planet in lots of ways. So for example, there's these are amounts in millions of tons of CO2 net transfers. There's a big flow from China to the United States because lots of products are manufactured in China, and the emissions take place in China. But these things, the atmosphere is mixed worldwide. But we also manufacture lots of stuff in the U.S. and send it over to Europe and so on. So you can see that there's a complicated interchange, and we need to really work on this around the world. It's also true that that we move lots of fossil fuels around the world. You can kind of see here, there's a big bunch of arrows that start here in Saudi Arabia and the Arabian Gulf or Persian Gulf, depending on which side of it you're on. There's quite a bit of flow around the planet that deals with all of that, and that's part of how we'll have to think about that in the future. So you say, okay, fine, we're convinced. Now let's do something about it. If we are not using the fossil fuels, or if we're using them in some other way that makes that lower in its carbon emissions, what do we do? What energy resources can we use? Well, the students here will be pleased to know that this will not be on the quiz. And I'm sure as heck not going to talk about every number on this slide. But what it's meant to, what it is a kind of a snapshot of how energy flows around the planet. There's a huge amount of solar radiation that comes in, and in the end, that drives almost all of what we have, because that's what supports the plants that got laid down, the organic material that eventually became oil and coal. It's what makes the wind blow. So the 162,000 terawatts came in. Some of it went right back out by the atmosphere, radiating back to space. Some of it gets to the surface. Some of it warms the surface. That's a good thing. We would be on a much colder planet if it weren't for that global warming. Some of it evaporates water. All the hydro resources come from that. It makes the wind blow. So there's an 870 terawatt wind resource that right now we only use a little piece of that. But there's the message here is that there really is there's no shortage of energy. There is plenty of it around. It's all about how we convert it from whatever primary energy resource it is into an energy service like electricity or warmth or any of the kinds of things that we do. Now, just to set the scale here, you can see here that these numbers are in terawatts. We humans use order of about 15 terawatts, and the ovals here are in the commonly used unit of zetajoules, and everybody, of course, knows what a zetajoule is, right? Well, okay, if you don't, we use about half of one of those a year. So it's okay. It just sets the relative scale, and all of these numbers on this slide are big compared to the amounts that we use here. So the problem is not the energy. So what do we do now? Well, and is it changing? This is U.S. energy, and you can kind of see the top part is primary energy production, and there's been a big transformation in oil production has really changed over the last 6 or 7 years in the U.S. Natural gas production has gone up, coal production has gone down, and the energy consumption, natural gas is a bigger fraction, petroleum is just about flat. And coal has declined a fair amount as well. Nuclear power really has stayed the same, but renewables are growing. So let's take just a moment and look at some of that. So, and this will be interesting to see if I can manage to stay on the stage while I do this. So if you look at the top emitters around the world, China has really grown very fast in recent years. U.S. has actually declined a bit. Europe has declined a bit. India is increasing as well. And these two these reflect the growing developing economies and are both a challenge and an opportunity. If you just look at the share of emissions from energy use and making cement. So cement is made from basically calcium carbonate rocks. What you do is heat it up, drive off a CO2 molecule, and you're left with calcium oxide, which then you later on react to make concrete. And it's enough to be on the map. Natural gas, of course, is here. And coal is here, but look, there's also just been a beginning of a drop there as well. So that's the kind of the challenge. I said that natural gas has increased in this country. There really has been a revolution in the last decade, but it was a revolution a long time in the making. It required the ability to drill long-reach horizontal wells, so this kind of magical control. It's like, in a way, it's kind of like taking a piece of spaghetti and trying to drill through Jell-O by pushing the spaghetti through the Jell-O. You go, wait a minute, this is never going to work. What does work, however, is to pull the drill sting through there, and then at the same time, these rocks, the shales, are ones that it's very difficult to flow through them. So the way you make it possible for the gas that's stored there to flow is you create some cracks in the rock. That's the hydraulic fracturing part. Those various pieces finally came together in the late 2007 or 8 range to create this shale gas revolution. And here's the big frac job that is cracking the rocks deep down underneath and a schematic of how this works. So it's really had an impact. Turns out there are lots of these shales around the world. Ours are deep marine shales that have lots of organic material in them. China's were There are lots there potentially, but they are not as productive as the ones here in the United States. So we're still kind of exploring how all of that is going to work. So you can say, okay, how is this changing the mix of energy that we're using? And the answer is partly slowly, because these are enormous systems. But you can see that if you just look at new power capacity additions by fuel, coal plants are still being built, but some are being retired, particularly in this country due to market forces. Solar PV is big, wind has been big, natural gas, some installations and retirements. So if you add up all the renewables, about 2/3 of the power capacity additions last year were renewables. Now, word of caution here. Capacity factor is what fraction of the time you actually use that resource. It's typically maybe 20% for solar, might be 35% for wind, might be 95% for a nuclear power plant. So if you weight these, this is what's on the nameplate capacity, not necessarily how much power it produces. But if you also look at energy consumption by energy type, you can kind of get a sense of the trends here. So coal, still growing, but perhaps the beginnings of a peak here. Oil still growing. Oil to first order is transportation. It's diesel fuel and gasoline. Natural gas growing fast. Nuclear pretty much flat. Hydro growing nicely, and other renewables 15.2% a year. So the renewables are growing fast, but they're doing it from a small base. So we need to kind of examine that and see whether can that continue and continue to contribute. And the answer is yes. And it's partly because there have been deep cost reductions over the past, now 9 years. If you just look at these are against the 100% in 2008, but wind is down by about 40%, utility scale photovoltaics by about 50%, batteries have dropped in cost, and LEDs are down now over that period by about 95%, 94%. So you go, wow, how did that happen? Well, part of how it happened was that we began to get to scale in manufacturing them. The first LED bulb I bought cost $60. You might say that was economically crazy, but hey, that's what I do, right? So, but at the same time, as the manufacturing took place a year and a half ago, India bought millions of these at about $1 each. And so it's the being able to learn by doing, figuring out how to manufacture at scale really did reduce the price. So you go, okay, that's a possibility. So what lies ahead? Well, the first point I would make is that we should work to improve energy efficiency everywhere. I'll give you a couple examples in a minute, but we have left ourselves a lot of room to do better in this country on energy efficiency. That's the politest way I can say that. We can do lots of things that will reduce energy use and at negative amortized costs. In other words, it pays more than pays for itself to do it. So you can ask yourselves, well, why don't we do it? And that comes back to this pesky humans that make decisions about things that are not always economically entirely rational. Then we should generate electricity with low carbon technologies, and there are lots of those. I'll talk about the various ones. We need to work on improving our grid because we need to accommodate a different set of services that go with the intermittent renewables. And we also need to work on bolstering resilience, as Puerto Rico and Napa Valley both have illustrated for us. We can electrify some energy services like transportation and using heat pumps more effectively. We can replace coal with natural gas, or we can deploy carbon capture and storage for either one of those. Or and I'll argue at the end that we need to be willing to do this, we could develop and deploy new energy technologies. So let me just take a moment and talk about each of these. If you look around this country, about 40% of all the energy we use ends up in a building somewhere. So you go, so that's a place that we ought to look. We could, with technologies that pretty much exist now, we could get that down by a quite substantial amount. And I can tell you the experience of my own house. When about 10 years ago, when I put in solar cells, they cost a lot more then, I wish I'd waited, but I looked at the energy use and sized the system, but while I was waiting for the panels to arrive and be installed, that made me go look at I got out my watt meter and I went around and measured everything in the house. And the stuff I couldn't unplug, I looked at nameplates. And so by the end of that, I had a pretty good idea where the electricity was going. So I could change the way I operated that machine. You know, I won't go into all the details, but with a capital investment of about maybe $100, I reduced our electricity use by about a third. And you know, I'm pretty sure I'm not alone. So there really is an opportunity. And there are lots of things we can do. Windows, lighting, you know, I just went through and in my house, I'd gone to compact fluorescents, but I'm now switching everything to LEDs. The heating and cooling and refrigeration, these are areas, particularly in the developing world, where there's a real opportunity to do better there. And by efficient building designs, our experience at Stanford has been that the incremental cost of designing and building an energy efficient building, maybe it's 2%. It's not much as long as you build it in from the beginning. So there really is an opportunity. And here I would say also that this whole question of sensors, we're, I think, entering sensor world. We're able to build less expensive sensors now. They can communicate wirelessly and less expensively. Now this causes this avalanche of data that we have to be able to think about how to use, but nevertheless, there are lots of opportunities for improving efficiency there. LEDs, I mentioned one of these. This is another version of deployment, and this has continued on up since this plot was drawn, and the costs have continued to decline. Let me say a word about what we did on the Stanford campus, because I think there's a lesson in this as well. So we noticed, first of all, we had a 50 megawatt gas turbine on campus, and it was combined cycle, and it was pretty good for its day. And we did a lot of, we used for heating and cooling. But we noticed that there was this overlap all year round of taking heat out of buildings with the cooling loop and putting heat back into buildings for various other kinds of services. Some in the wintertime is heating the building, but there are all those other. So instead, basically what we did was to replace the combined cycle plant. It was at the end of its life, and we needed to work on a leaky, creaky steam distribution system as well. And the basic idea is you take this heat out of where you're cooling, you take the heat out of buildings. So let's push that back with the heat pump back into the heating side and not buy fuel to do that. It saves about $400 million over 30 years from reduced fuel purchase and reduces water use, which for us is a big limitation, by 18%. So you go, well, all right, this sounds pretty good. How do we do that? So there's a set of heat recovery chillers. These are just big heat pumps is what they are. They're various natural gas fired hot water generation, so there's a little bit of gas heating here. And then there's some cooling towers as well. So we can put that together, and they also worked on a very cool control system that really helps things as well. And the fundamental reason for this is that if you just use electric radiant, this is basically how your toaster works, right? Because of the big, the thermodynamic hit that comes when you make the electricity, and then you turn that back into heat. That one may be used as 7 units of gas for the service. You can heat directly with gas, that does 4 units, but if you use a big electric heat pump, you can use 1 to, even paying for the electric power it takes to do this with natural gas, you can use 1 to 2 units of gas, and if you're willing to put some solar or wind into that as well, you can reduce it further. So what this did was to give us this is actually measured to so far a 50% reduction from 1990 levels and 68% from peak in our greenhouse gas emissions for the campus. So, and I note again that it saves hundreds of millions of dollars over the next, so this is a project which pays for itself over time and by a big amount. So what about clean electric power? Well, obviously wind we can use. This is growing rapidly. It's about 5.5% of U.S. electricity, but it was 4.5% last year. So this is growing. I mean, adding 1% of the electric power generation for this country in a year, that's a big deal. And it is 77,000 jobs in 2015. There are just lots of research opportunities for how these things can be done. But, you know, it turns out that if you can steer the wind turbine, which you can so that you line it up in the wind, you can actually steer the wakes so they don't interfere with the other wind turbines that are nearby. Now, this takes lots of computational power to be able to figure out how to do this, but there are remarkable things that we can do there. On the solar generation side, costs have come way down. There are lots of jobs associated with this. The concentrating solar power allows for, because you're turning that into heat, thermal energy, you can store that in a tank for the part of the day when the sun's not shining. So we've made big cost reductions, but we can still go quite a lot further here. And I'm not going to talk, I'll talk a little more maybe about the technical details in a moment, but the one thing that, so just at the end of my time at DOE was, it's pretty clear that we're going to make the sunshine goal for 2020 is 6 cents a kilowatt hour. We're about 7 then, so we'll make that actually before 2020. But then we said, well, okay, what else can we do? And we eventually, it took some effort, but we eventually convinced the secretary that there were multiple pathways to get to down into the 3 cents a kilowatt hour and maybe even 2. And you say, well, gosh, I mean, that's really competitive, and why do you want to do that? Well, the answer is because if you get to those kinds of costs, then you can afford to do another transformation that involves energy storage. It could be liquid fuels. It could be all kinds of things that gives you some room to do that. And now, I don't mean to minimize the difficulty of doing this. There's lots of options. You can see the module prices, the balance of system hardware and installation costs, lifetimes, operations and maintenance, and so there are lots of things to do here, and we did lots of analysis of each of these. And you say, well, okay, what are the options? Well, I'm not going to try to go through all the details here, but over the last 15 years, a project that I worked on at Stanford really invested in the fundamentals of all this. And in that period, we just put together one cool idea after another of ways to manage light, ways to get lots of light absorption, but easy ways to catch that electron before it recombines with the hole. If that happens, you have a warm solar cell, but you don't have any electricity. And these new things called perovskites that have just rocketed into our attention of ways to generate more efficient electric generation in using advanced material science. So if I picked out one area that really applies across almost everything, it's the material science side of things. And if you look at the International Energy Agency's estimates of future costs, so the future starts right here. This is quite a recent report. But even these are based on power purchase agreements that for delivered costs and long-term contracts. So these are real data, and they show continuing declines of cost. They're not as low as the ones I showed here, but they nevertheless, in places where you don't have a grid access, this really makes a big difference. What about the nuclear side? Well, about 19% of the current U.S. electric power generation is from nuclear. It's base load. It's these plants are run 90-odd% of the time. And you say, well, great, you know, is there an issue? And the answer is there is an issue, and it's cost. These plants are having a hard time competing in areas where the dispatch is based on a bid system, and natural gas can supply this electricity at a lower price now. So some of the plants are struggling. There is one possibility on the horizon that might make a difference here. It remains to be seen. That's a small modular reactor. There's a kind of a mock-up of what one might look like here. There's a company called NuScale that has just submitted an application for design certification. And they have agreements for the first couple of these reactors to be installed. They come in 50 megawatt lumps, not in 1,000 megawatt lumps. So the cost per watt is about the same as a big nuke, but you don't have to lay out $8 or $10 billion to buy one of these. So if you bought my argument about getting to scale, having smaller unit costs is one way to try to deal with that problem. There are plenty of research kinds of things going on as well, but they are much farther out, and they require big government investments because they're so expensive to do. Waste storage, siting, and licensing and construction costs are all still big issues. There is a fair amount of construction going on around the world. China is building 24 plants right now. So the situation in the United States is not exactly the same as elsewhere. On the carbon capture and storage side, you know, we capture commercial quantities of CO2 every day. In refineries and natural gas purification, so you can sell the gas. These are mostly done with solvents. They're amines of one sort and another. The real problem is cost. And so there are lots of cool things. I'll talk more about this tomorrow, and there's some very interesting things going on here at BYU that it's fun to think about how those can contribute. You then take that CO2 and put it into the subsurface. We have a lot of experience. We've been doing this for enhanced oil recovery since the early 1970s. So we have a lot of experience of what happens in the rocks underneath. You have to choose sites well and operate safely, but when that's done well, we can put the CO2 there and keep it there. Now, there was a very big DOE-funded project at a plant called Kemper, which was a gasification project, combined cycle, plus carbon capture, and then using the CO2 for enhanced oil recovery. It had lots of cost overruns, and this was a pretty complicated sort of 5 chemical plants put together, and they could never get all the pieces to work right. And finally, the state Public Utilities Commission caused them to switch from lignite to natural gas in June due to the startup delays and cost overruns. So that was a bit of a blow. So we'll see. There's more to be done there. But I would note that on the natural gas side, just replacing an old coal-fired power plant, steam plant, with a combined cycle gas turbine, there's less carbon in the fuel, and the efficiency of the power plant is much higher. And so therefore, you get an almost 70% reduction in CO2 per kilowatt hour just by that switch. And if you use a single cycle turbine, you're still in the almost 50% range. So there is a big benefit, and this is being, as I said, being driven by the market at the moment. So let me say a word about the grid. So here's the old grid. You had a bunch of big power generation facilities, largely radial distribution out to customers. And that is changing because we're starting to have more distributed control, and eventually we'll have a system that's got lots of distributed generation, lots of intermittent renewables, lots of those of us, generating in high-cost electricity cost areas, generating our electric power at home and selling it back to the grid. And of course, there'll be all those smart meters that are actually sensors that tell the operator whether there's power where I am. It used to be that they had to drive around in a truck and shine their flashlight and look to see where the tree had fallen on the wires. Now they can tell that by which smart meters are reporting back, at least in the places where the smart meters are all connected up. So there's really a lot of potential to provide much better services and faster recovery when we have problems, provided we do this in the right way. Now, this is not without some challenges. So in California now, we have enough installed wind and solar that in the middle of the day, we can cover a quite remarkable fraction of the power generation during the day. But of course, as the sun goes down to low in the horizon in the late afternoon, and our wind resource is bigger at night, and that hasn't picked up yet, we can get some pretty astonishing ramp rates of power needs into the early evening. Now that's accommodated by natural gas, and that certainly can be done, but you have to think about balancing all those systems. Now one option there is to think about more storage, and there's lots of work going on here. And the thing to remember is that the storage issue for batteries in an electric car is pretty different from the grid scale part of this. And there are a whole bunch of things being tried for really bulk power. Pumped hydro is the only real game in town. Compressed air energy storage has been talked about, but has really not been deployed. But pumped hydro has great round trip efficiencies, much better than batteries. But you have to have a hill and a big place to put the water. That might not be a problem here in Houston. Well, they had their own problems with where to put the water, but it wasn't at a high elevation, I can tell you that. That's where I grew up, and my neighborhood was underwater. So I'll just say that this is a huge area of research. It's fundamental material science, it's chemistry, it's chemical engineering. It's just full of interesting problems to be worked on. So there's a lot to do here. And so let me kind of finish just with in a way, this is a sort of a speculation. So in the last 6 months that I worked at DOE, we asked ourselves, well, okay, suppose we manage to meet all the goals that we have for the various energy technologies, the solar, the wind, and so we then use the so-called NEMS model. This is a National Energy Modeling System. Sometimes it was hard to convince the model to what do you do about battery electric vehicles. There was no knob for battery electrical vehicles. So we had a variety of challenges to just get this into the model. And then we said, well, if we did a projection of CO2 emissions, this was kind of the business as usual as we are now. But if we met all the advanced technology goals, you can see that's the kind of darker blue line. And then we cooked up some goals that we call stretch tech. Now, there was a big argument, I'll tell you, about how plausible some of these were. So I wouldn't bet your future on any of the details here. But nevertheless, we could see that had an impact. And then we did a couple of cases of using a quite small carbon price as a proxy for other regulatory kinds of things that might happen. And the net result was with those together, there was an interaction between the policy side and the technology side that got us well down the road on the kinds of reductions we would need to get to to have a reasonable probability of staying in the 2 degree C climate change regime. But the situation was pretty mixed. We could see pathways for pretty deep carbon reductions in the building sector. This is largely due to better electricity, so that helps. Transportation is much harder, even with lots of deployment of electric vehicles. It's tougher, and the industrial sector was tougher too. So there's some big challenges there that we have to meet, but it's not hopeless. One of the things we did for industry was to kind of look at sort of, well, this one was refining. We did this a lot for lots of industries. We could make significant near-term efficiency gains with lots of different technologies. And there were some good R&D opportunities for more. Thermodynamics limits what you can do entirely, but there's a big potential thing to do here, and there's plenty of room for creative research on all of our efforts. So let me then, I'm just about to stop, but I'll just say that internationally, we have made some progress. The commitments made at the Paris Agreement get us kind of halfway there of what we need to do to stay within the 2 degree C goal. U.S. made a commitment of 26 to 28% below 2005 by 2025. The current administration's view is that this isn't in our national interest, so I don't know if we'll get all the way there. Well, a lot of this will happen anyway because it's being driven by market forces. China is going to hit their peak of their commitment earlier, I think, than they committed. And the other 194 countries have issued plans with varying levels of ambition, and so those offer a real opportunity to go forward. Now, as I said, we've announced that the U.S. will withdraw. You can probably guess that I think that's a mistake. But a whole lots of state governors, mayors, company CEOs, and so on responded, well, we're looking at the long term here and we can see what's coming, and we're going to meet our goals and try to make those be more ambitious anyway. The Clean Power Plan is now likely to be withdrawn, but even there, a lot of the states will meet their commitments, including Texas, which is, but they said, but it's not because they made us. We're a combination of natural gas and lots of wind. Texas is a big leader in wind. So I think we'll continue to reduce our emissions, and then other countries will continue. So I think this will be important. So let me finish here. I think a clean energy transformation is well underway. We've made some progress, but there's a heck of a lot more to do. And in particular, it's all of you students in the audience who are the ones that we have to do. We have to do this, stick with this, do it everything we can now and stick with it over an extended period, but there's a huge opportunity space. It should be a portfolio. It needs to be fully diversified across primary energy resources and all the ways we convert those into energy services, but that just gives us this magically broad set of opportunities to do better. There needs to be efficiency everywhere, and by the way, there's a pretty big market out there for this. The world will spend $60 trillion on energy infrastructure until between now and 2040, and at least a quarter of that, and I would argue more, is going to be the clean energy side of things. So there's a pretty big market out there for countries that do a good job on this to lead the way. So I'll just finish by saying we can do this, so let's get to work. Thank you very much. Whoops, I see I'm probably about out of time, but I'm happy to try to respond to questions. Here.
Yeah, so if in transportation, increase renewables which are intermittent?
Yeah, so the question for those, for the video is that what do we do if we really do shift transportation to electric vehicles? What do we do about baseload? And the answer is that that's one of the big challenges. In principle, you can balance, if you have enough natural gas and nuclear, you can balance the intermittencies and throw in some storage if you like as well. Saying that and doing that are not the same. It's going to be a very different and complex system. I think it helps to have some nuclear in the mix on that. We'll see if that continues. But there's now starting to be enough experimentation on the assorted ways to do this, and that includes revising the market structures of how we bid for capacity as well as for actual delivery of kilowatt hours. That I think we'll see some substantial changes, and the utility industry is probably going to have to evolve quite a bit as we do this. So big challenge, lots of ways we can work on it. In the front here, and then we'll go back there next.
So looking at all the different people that are working on in the U.S. or abroad.
Okay, so there are lots of market actors, universities, companies, and so on, governments, regulatory structures. Which one has the most influence? Gosh, I wish I knew the answer to that question. This is just wonderfully complex. I mean, the standard joke is that people complain that we don't have a national energy policy, but we do. It's determined by 50 public utilities commissions in the states. That's where decisions get made in regional, the grid is managed in regional balancing authorities. It is wonderfully complex, much of the regulatory side, I mean, we regulate air pollution emissions, but we don't really regulate how individuals make consumer choices. So consumers are a big part of this as well. And I don't think there is a clear answer to you. I mean, I don't think any one of this is I heard a utility executive the other day say, if our customers demand that we produce lower carbon energy, we will do it. And he says, my customers do demand that, and we are doing it. So we consumers have a role to play in all of this as well. And I would just say to the students here, the ones that didn't have to rush off to the next class, that there's lots of technology work to be done here, but that's by itself not enough. We need to think about market structures. We need to think about the regulatory side of things. Some of those market structures protect the incumbents. And so we need to make it possible to innovate here in ways that aren't always as easy to do as they could be now. So there's human behavior. Gosh, the hardest part of all of this is figuring out what we pesky humans are going to do with regard to choosing how we use energy. So there is room for really interesting work across that full spectrum. Then there was one back here.
So in regards to who pays
Who's pays? Well, so it's a very good question. The question is who bears the cost of energy storage? And in the end, the customers of the utility system have to bear that cost. Now, how we do that and how you price the service that a customer provides. There's some proposals, for example, to use all of us who drive electric vehicles to use our batteries to do some system balancing. And I go, hang on a second. I know what charge and discharge cycles do to the I'll need to be compensated for the capital cost of replacing that battery sooner. So, and I don't have an answer to your specific question yet, because this is definitely all very much in discussion. California, which has a big fraction of renewables, Hawaii is in a situation where they're really trying to figure out how to price all this stuff. There won't be a central policy for the whole country. There'll be a lot of experimentation at the state level, and I think we'll learn from that what works well as a market structure and what doesn't, but it's too early to give you a good answer.
You indicated that and all that.
Yeah. So the question was, I claimed it was wonderfully complex. Is there security that comes from that complexity? And the way I would say, I would use a different word. I would say the security comes from the diversification that is, the complexity is part of that. But the word diversified, maybe it didn't actually get on the conclusion slide here, but that I do absolutely think you don't want to put all your energy eggs in any one bat. You want a diversified system for exactly that reason. It is more stable and more secure if you have that.
With wind and some of the
Sure. So the question is, wind is profitable and other technologies only because they're subsidized. It is true that the wind enjoys a production tax credit now. It will sunset here in the early 2020s. So the deal in Congress for that extension of those subsidies calls for that. In the end, these technologies must compete on their own. And the one thing I would say is that we have been wonderfully inventive in the way we apply subsidies to pretty much all the energy technologies of one sort or another. They all have their own versions of this, and we don't do a very good job of rationally balancing all of them. Wouldn't it be good if we worked on that across the board? But I think you're exactly right that, there's this argument that with the subsidies help you get to scale so that you can really drive the cost reductions. And I think that there is support for that part of the argument. I can see that it's time to go. Thank you all for your attention.